Hi everyone, welcome to this video. I am a digital presenter from the Biosystems Control and Computation Group led by Zhou Fang at the Chinese Academy of Science. In this episode, I will introduce the group's recent work on effective filtering approach for joint parameter state estimation in stochastic differential equations via Rao-Blackwellization and modularization. This is a joint work by Dr. Zhou Fang, Dr. Ankit Gupta, and Professor Mustafa Khammash. Stochastic filtering is a popular topic in the control and statistics field, which aims to utilize partial observations of dynamic systems to infer and recover the full dynamical states and system parameters. With an accurate solution to the filtering problem, scientists can accurately monitor the system under investigation and gain a better understanding of its mechanisms. Additionally, it allows for better control strategies to drive the system to a more optimally functioning phase. These capabilities are particularly important for the analysis and control of uncertain systems, including the global climate system, spacecraft, as well as biological systems, which we are most interested in. So far, filtering approaches have been successfully applied to all these fields, enabling big breakthroughs. Despite these successes, existing filtering approaches face big computational challenges when they are required to estimate both parameters and states for nonlinear systems. This arises from an issue called sample degeneracy, which we will discuss in detail later. Notice that joint parameter state estimation is common in many practical applications, including biological filtering problems. Consequently, this challenge significantly limits our ability to analyze and control real-world systems. In this talk, I will introduce an effective approach to address this issue by leveraging Rao-Blackwellization and modularization. In this work, we consider SDE systems described like this. Here, xt is an n-dimensional vector representing the system states. Each element of x of t represents one degree of freedom, whose dynamics are influenced by an unknown parameter, theta I, the whole system state x, a known parameter sigma I, and a Brownian motion bi. The considered system is then measured at a discrete time series with the observation y satisfies this relation. Here h is a known function and w is white noise. With these notations, stochastic filtering aims to compute the conditional distribution of the parameter theta and the system state x, given the observations up to the current time. By the Bayes rule, the filtering problem can be solved recursively through prediction and correction steps. Specifically, at each measurement time tk, one can use the filter at time tk along with the transition probability to compute the conditional distribution of the system state at the next time tk plus 1, given the observation up to the current time tk. This corresponds to a prediction step which uses all the obtained observations to predict the future state. Once the prediction probability is obtained, one can further adjust it according to the observation at the next time to obtain the filtering solution at time tk plus 1. By recursively doing these prediction and correction steps, we can solve the filtering problem at every measurement time. When the considered system is linear and Gaussian, these recursive formulas yield Gaussian distributions as solutions. In this case, we only need to track the conditional mean and variance of these conditional distributions. This approach corresponds to the famous Kalman filter. In contrast, when the system is nonlinear, the recursive formulas often have no explicit solution. In this scenario, we can solve the filtering problem numerically using the Monte Carlo method. This corresponds to the famous particle filter, which uses simulated particles to make predictions and corrections. In each time period, the particle filter simulates all the particles according to the dynamical equation, whose empirical distribution then approximates the prediction probability. afterward, the particles are re-weighted according to the observation at the next time point, so that the empirical distribution of the re-weighted particles approximates the filter at the next time point. In the end, the filter resamples the particles to reproduce important particles and delete insignificant ones. The particle filter performs nicely for many applications. However, when applied to joint parameter state estimation, it suffers a problem called sample degeneracy. This problem arises from the resampling step. Specifically, the values of the parameter particles theta j are unchanged in the prediction step, as shown in this figure. Then the resampling step will delete some of these particles and reproduce others. Consequently, after each iteration, the number of distinguished parameter particles is often reduced, as shown in this figure. In the end, the parameter particles converge to one or two values. In the top right plot, we show how the number of distinguished parameter particles fast decays over time in an example. The blue and red dots represent results from two numerical trials. One idea to improve the number of distinguished parameter particles is to perturb the particles after the resampling step. Such a strategy has been used in the regularized particle filter, nested particle filter, and so on. Basically, after being perturbed by some artificial noise, the initially identical parameter particles become different, as shown in this animation. However, this strategy also faces the challenge of selecting an appropriate noise intensity to perturb the particles. If the noise is too strong, it introduces a too large bias into the estimates. On the other hand, if the noise is too weak, it fails to effectively address sample degeneracy. Overall, joint parameter state estimation is a challenging task. This problem seems to originate from the existence of parameter particles. With these observations, we ask the question, can we have a method that avoids generating parameter particles? The answer is yes. We can use Rao-Blackwellization, also known as the marginalized method, to tackle this challenge. The method is based on the law of total expectation shown here, which says that the filtering problem can be solved by generating particles of the system state X and the conditional distribution of the parameters given the state and observation trajectory. In this way, we can avoid the generation of parameter particles. Actually, this method has been successfully applied in continuous time Markov chains. In this reference, Zechner and his colleagues applied this exact idea to analyze biological systems described by Markov chains. In one of our recent works, we further extend this method for gene expression systems by marginalizing out some state variables, in addition to parameter variables for further improved accuracy. Here are the results from our recent Nature Communication paper, which shows the good performance of Rao-Blackwellization in continuous time Markov chain and its application to investigate noise decomposition in a yeast cell population. Now, in this work, we aim to extend the Rao-Blackwell method to SDE systems. The key is to derive the dynamical equation describing the evolution of the conditional distribution, specifically the red term on the slide. According to the filtering theory, we can show that the unnormalized density of this conditional distribution satisfies a Zakai equation of this form. Thanks to the good structure of this Zakai equation, we can obtain an explicit expression of its solution under some mild conditions. Moreover, when looking into the solution, we can observe that this solution is a product of marginal densities, indicating that all the parameters are conditionally independent. This fact also suggests that when numerically computing the conditional parameter, we only need to construct the marginal ones instead of the joint one, which allows for great computational efficiency, especially when many parameters are involved. With these derivations, we can now provide the Rao-Blackwellized particle filter for SDEs. As mentioned, This method generates particles for the state variables and the conditional distribution of parameters. Compared to the classical particle filter, the new algorithm needs to additionally update the conditional distribution according to the solution of the Sakai equation. Also, the filter is computed according to the law of total expectation. These changes compared to the classical bootstrap filter are highlighted in red. The convergence of this algorithm is ensured by the convergence properties of the general Rao-Blackwellized particle filter, demonstrating the reliability of the approach. Now, we demonstrate the effectiveness of our approach in a couple of numerical examples. First, we consider a stochastic Lorenz 63 model, which is commonly used to test the performance of a filtering approach. The dynamical systems and the observation are listed on the top left. The numerical results of our approach are presented on the right, showing the accuracy of our method in estimating both the system parameters and states. We also compared our approach with other competing ones in estimating system parameters in the bottom left panel. It demonstrates that our method, indicated by the red dots and lines, is the most accurate in estimating the actual system parameters, indicated by the dashed line. Even though other approaches can also relatively accurately estimate all the parameters in certain situations, they require a very careful selection of the artificial noise for perturbing the particles, which is almost impossible to know in advance. In the second example, we consider a stochastic ecological model described like this. Here, x1 and x2 represent prey and predators, exhibiting oscillatory dynamics. In this example, our method can again accurately estimate both the system state and parameters. In contrast, other approaches can only have good performance when the artificial noise is finely tuned. Overall, our approach outperforms other ones in both numerical examples. To conclude, we present a Rao-Blackwellized particle filter for joint parameter state estimation in stochastic differential equations. The approach is more accurate and robust than existing approaches, as the generation of parameter particles is avoided. We have also developed a method for more general SDEs, where unknown parameters also appear in the diffusion terms. The extension paper was recently submitted. There are also several topics that need to be further explored in future work. We list them here. That's all my talk. Many thanks for your attention.